Namaskar. Today we will discuss about Amphibolite facies. The Amphibolite facies belong to intermediate pressure temperature facies. If suppose we will see on the screen the intermediate pressure facies, that is Geolite, green schist, Amphibolite and Gyanolite facies. Amphibolites comes after green schist facies. Amphibolite facies, the important contents are introduction, second is your zone oblique subfacies, Staurolite zone, important reactions, mineral assemblages, Kyanite almandine zone, mineral assemblages, Sillimanite muscovite zone, mineral assemblages, Sillimanite orthoclase zone, mineral assemblages, physical condition of metamorphism, and lastly conclusion. So, now take up the first module, that is introduction. On the basis of pressure and temperature, we can divide the metamorphic facies into three types, mainly facies of low pressure, facies of intermediate pressure and facies of high pressure. Mayosiro originally recognized three different facies series, that is a Geolite, Prehnite, Pumpelite, blue schist, eclogite type. Second, a typical Barrovian type characterized by green schist, epidote amphibolite, Amphibolite, Gyanolite type characterized by paragenesis of Kyanite, Sillimanite type. And third, an Abukama type of green schist, Amphibolite, Gyanolite characterized by paragenesis Andalusite Sillimanite type. The Abukama type is named after the Abukama region in Japan, and it is similar to the Buchan type of Dahlildian. The facies of intermediate pressure in order of increasing temperature and pressure of metamorphism. First is Geolite, second green schist facies, third is Amphibolite facies, and fourth one is Gyanolite facies. The diagnostic mineral assemblages restricted to this facies are hornblende plesioclase, anorthite nearly 15%, almandine, and hornblende plesioclase, anorthite 15%, epidote. The appearance of any of the following minerals is decisive for the identification of Amphibolite facies, that is Staurolite, gracilorite, andradite, diopsite, cummingtonite and anthophyllite. Furthermore, white mica, which approaches phengite in composition in green schist facies, change to muscovite, abundance of almandine, Staurolite or Kyanite, and absence of corderite and andalusite distinguish Pelitic assemblages of the Amphibolite facies from those of the hornblende hornfels facies of lower pressure metamorphism. We can divide the intermediate pressure facies into four different zones, that is your Staurolite zone or Staurolite almandine subfacies, Kyanite zone, Kyanite almandine muscovite subfacies, and third is your Sillimanite muscovite zone or Sillimanite almandine muscovite subfacies. Fourth one is your Sillimanite orthoclase zone or Sillimanite almandine orthoclase subfacies. Now take up the first zone, that is your Staurolite zone oblique Staurolite almandine subfacies. The transition from the green schist to Amphibolite facies is best recognized by the diagnostic first appearance of Staurolite and disappearance of chlorite and chloritoid in the presence of muscovite and quartz. The reactions are: first reaction, the chlorite plus muscovite plus almandine garnet give rise to Staurolite plus biotite plus quartz plus water, which occur at 540 degree centigrade 4 kilobar 565 degree centigrade 7 kilobar, carried out by Hosek 1969. The second reaction is your chloritoid plus kyanite give rise to staurolite plus quartz plus water at 540 degree centigrade 4 kilobar, carried out by Hosek and Richardson 1968. The third reaction is chloritoid quartz, staurolite plus almandine plus water, temperature 15 to 30 degree centigrade higher than the reaction 1 and 2, carried out by Ganguly 1969. Presence of staurolite along with kyanite is a diagnostic of this phases. Staurolite appears in those that are richer in Al2O3 and FeO and poor in alkalis, as shown by the Hosek 1967. Important reaction: the impure calcareous rocks, diapsite and gracilorite form by the following reaction. Reaction number 4, that is tremolite plus 3 calcite plus 2 quartz give rise to 5 diapsite 3 CO2. Reaction 5, epidote plus quartz give rise to gracilorite plus anorthite plus 2 water. And reaction number 6, 2 epidote plus 5 calcite plus 3 quartz give rise to 3 gracilorite oblique andradite plus SiO2 plus water, which occur at 500 degree centigrade 2 kilobar, 575 degree centigrade 4 kilobar by Nis 1973. Furthermore, amphipholite appears in magnesian assemblages. Reaction 7, talc give rise to amphipholite plus quartz plus water. For pure Mg system, the above reaction has been investigated by Greenwood 1963, who found the equilibrium temperature at 607 degree centigrade 1 kilobar, while for a system in which Fe ratio Mg is 6:4, the reaction occur at much lower temperature, that is 520 degree centigrade 1 kilobar by Henrichsen and Seffert 1965. Amphipholite also appear by the reaction. Reaction number 8 is your tremolite plus chlorite plus quartz give rise to hornblende plus amphipholite plus water, which occur at 560 degree centigrade 2 kilobar, carried out by Chaudhary and Winkler 1966. The Pelitic rocks. The first assemblage is your kyanite plus staurolite plus biotite plus minus muscovite plus minus quartz plus minus plagioclase. The second assemblage is your staurolite plus biotite plus almandine garnet plus minus muscovite plus minus quartz plus minus plagioclase. And the third important assemblage is your almandine plus biotite plus minus muscovite plus minus quartz plus minus plagioclase. Quartzo-felspathic assemblage. Assemblage 4 is your quartz, microcline, plagioclase, biotite, muscovite. The another important assemblage is your basic assemblage. The assemblage number 5, hornblende plus plagioclase plus almandine garnet plus minus epidote plus minus quartz plus minus biotite. Assemblage 6, hornblende plus plagioclase plus minus epidote plus minus quartz plus minus biotite. Assemblage 7 is your hornblende plus diapsite plus plagioclase plus minus epidote and plus minus quartz. The derivatives of basic rocks are amphibolites. Many of them are garnetiferous, coexistence of plagioclase, anorthite 25 to anorthite 45 with epidote commonly presence in these rocks. Now, the next assemblage is your ultramafic, ultrabasic or magnesium assemblage. The assemblage number 8 is your cummingtonite plus hornblende plus almandine. Assemblage 9 is your cummingtonite, amphipholite, tremolite. The next important assemblage is your calcareous assemblage. The assemblage number 10 is your calcite, diapsite, gracilorite plus quartz. 11 number is your calcite plus diapsite, tremolite plus minus phlogopite. Assemblage number 12 is your diapsite, gracilorite, plesioclase plus phlogopite. On the basis of intermediate pressure and temperature facies, we have the idea about geolite facies, green schist facies, and now today we are discussing about amphibolite facies. We have already divided the amphibolite facies on the basis of index mineral based on Barrovian zone, that is Staurolite zone, Kyanite, Almandine zone, Sillimanite muscovite zone and Sillimanite orthoclase zone. If suppose we see on the screen the ACF, AKF, AFM diagram of all the 4 different zones, we can observe different assemblages, particularly the Pelitic, quartzo-feldspathic, calcareous, basic and ultrabasic. If suppose we will move from Staurolite towards Sillimanite orthoclase zone, there is a major rock type change which is schist to gneissic rocks. As soon as the Sillimanite form by the breakdown of kyanite to Sillimanite at higher temperature. Sillimanite is a higher temperature polymorph of your aluminosilicates. As soon as the kyanite transfer to Sillimanite, the nature of whole rock is changed, that is your gneissic in nature, where we can observe the different bands alternate light and dark colors, and the nature of rock is changed, that is your gneissic. If suppose we will compare the calcareous, basic and ultramafic assemblages, they are almost same as in case of Staurolite zone, means very similar to Staurolite zone, right from Staurolite to Kyanite Almandine zone to Sillimanite muscovite zone and lastly the Sillimanite orthoclase zone. The except change, major change is your Pelitic assemblages. Usually one very important question is asked in all the examinations. The question is, give a detailed account of regional metamorphism of Pelitic rocks. Then we have to describe this question on the basis of detailed studies of geolite, green schist, amphibolite and gammalite facies, mainly with respect of Pelitic rocks. So we can say right from Staurolite to Sillimanite orthoclase zone, the nature of rock changed from different type of schist to gneissic rocks. This corresponds to the kyanite isograde of Baroque. Staurolite is now no more stable. It reacts with quartz in the presence of muscovite to form almandine plus kyanite plus biotite. The reaction is your Staurolite plus muscovite plus quartz give rise to kyanite plus biotite plus almandine garnet plus water, which occur at 575 degree centigrade 2 kilobar, 675 degree centigrade 5.5 kilobar, carried out by Hosek 1969. The reaction has been revised by Hosek and probably the temperature given are higher. Thus, the disappearance of Staurolites provide the only possibilities of the differentiating between the subfaces oblique zones 1 and 2, it is evident that the critical association kyanite plus almandine garnet is now possible, which gives the subfaces its name. It is also obvious that in this subfaces, kyanite is much more common as compared to the staurolite almandine subfaces or staurolite zone, because the range of chemical composition from which kyanite now form is much larger here. Now, the next important thing is your mineral assemblages, the characteristic Pelitic assemblage. See on the diagram ACF, AKF and AFM diagram of Amphibolite Facies. Now, we can observe the Pelitic assemblages. The assemblage number 1, that is your kyanite, almandine, biotite, muscovite, quartz, plesioclase. Second is almost same as in staurolite zone, and third is your almandine, biotite, muscovite, plus minus quartz, plus minus plesioclase. Other assemblages are same as the staurolite zone mentioned already, that is your basic, calcareous and ultramafic. The mineral assemblages of this zone oblique subfaces are similar to the kyanite zone. Here the kyanite is replaced by the higher temperature polymorphs of aluminosilicates, that is sillimanite. So, better you replace the kyanite by sillimanite in all the diagrams. The important mineral assemblages, the typical Pelitic assemblages are number 1, sillimanite, almandine, biotite, muscovite, quartz, plus minus plesioclase. Second is your sillimanite, almandine, plesioclase, and third important assemblage is your almandine, biotite, muscovite, quartz, plesioclase. Muscovite, which was present throughout the range of metamorphism from green schist to sillimanite muscovite zone of the Amphibolite Facies, now becomes unstable. It is with this breakdown of the muscovite that the sillimanite orthoclase zone begins. The following reaction takes place. Reaction number 10, muscovite plus quartz give rise to orthoclase plus sillimanite plus water, which occur at 595 degree centigrade 1 kilobar, 640 degree centigrade 2 kilobar by Day and Chatterjee 1974. With this reaction, sillimanite is much more common as compared to the preceding zones, and now it coexists with orthoclase. The orthoclase KAlSi3O8 polymorphs of microcline is also transferred to higher temperature orthoclase. Furthermore, under the pressure and temperature condition of this zone, partial melting or anastasis of Pelitic rocks take place, as demonstrated experimentally by Tuttle and Brown 1958, Winkler 1967, 1974 and others. Please see on the screen the diagram where we can see the partial melting phenomena, the breakdown of the muscovite by the important reaction muscovite plus quartz give rise to orthoclase plus sillimanite plus water, the release of water, and at the same temperature the granite also melt. So, that is the indication of partial melting or formation of megmatites. In other words, also we can say, even in field also we can observe this thing. Thus, megmatites veined gneisses or lit perlite or injection gneisses are common. Some typical Pelitic and quartzo-feldspathic assemblages. First is your Sillimanite, almandine, orthoclase, biotite, quartz. Second important assemblage is your Sillimanite, orthoclase, plesioclase, biotite, quartz. And third important is your orthoclase, plesioclase, biotite, quartz. One thing I would like to say here, whatever we have observed from green schist up to kyanite almandine zone of Amphibolite Facies, we have observed the different type of schist like chlorite schist, chlorite chloritoid schist, biotite schist, garnet, biotite, kyanite schist, staurolite schist, staurolite kyanite schist, staurolite garnet schist, and kyanite garnet schist, etc. Now, the schist is no more stable, and with appearance of Sillimanite, the rocks change towards gneissic in nature, where we can observe in field as well as in lab the different layers, that is, we can say, the alternate light and dark colors. On the basis of that, we can say, yes, it is a gneissic nature of a rock in field as well as in hand specimens. That indicates the higher pressure temperature condition and more deformation as compared to schistose rock. The physical condition of metamorphism can be explained with the help of low and higher temperature condition and the same way pressure condition too. The lower temperature gives the idea about the beginning of the Amphibolite Facies, and the higher temperature gives the idea about the beginning of Kyanite Facies. Lower temperature limit. The appearance of staurolite is one of the most reliable indicator of the beginning of the Amphibolite Facies. Staurolite is formed by the following reaction: chlorite plus muscovite plus almandine garnet give rise to staurolite plus biotite plus quartz plus water. In fact, these reaction are bivalent reaction. If staurolite change towards chlorite, that indicates your retrograde metamorphism or retrograde reaction, and similarly if chlorite change towards staurolite or formation of staurolites indicates your prograde reaction, which occur at 540 degree centigrade 4 kilobar, 565 degree centigrade 7 kilobar, carried out by Hosek 1969. Another important reaction is your chloritoid plus kyanite give rise to staurolite plus quartz plus water, which occur at 540 degree centigrade 4 kilobar to 7 kilobar, carried out by Hosek 1969, Richardson 1968. Upper temperature limit. The upper temperature limit is indicated by the following reaction: muscovite plus quartz give rise to orthoclase plus sillimanite plus water, which occur at 545 degree centigrade 1 kilobar to 622 degree centigrade 3 kilobar, carried out by Rover 1975. Another important reaction is your MgFe amphiphyllite give rise to hypersthene plus quartz plus water, which occur at 735 degree centigrade when Mg/Mg plus Fe ratio, that is xmg equal to 0.6, and which occur at 775 degree centigrade when this ratio equal to 0.8. Mg Amphibolite equal to give rise to inertite plus quartz plus water, which occur at 745 degrees centigrade 1 kilobar by Greenwood 1963. Thus, the temperature condition in the Amphibolite facies is considered to be in the range of 500 to 550 degrees centigrade to 750 degrees centigrade. The pressure condition in the Amphibolite facies is determined by the triple point of Al2SiO5 polymorphs. We have already seen that in the Amphibolite facies, kyanite form first and it is replaced by higher temperature sillimanite. This demonstrates lower temperature and pressure condition during the metamorphism must be above the triple point of Al2SiO5. So many workers, they have carried out the experimental work about the stability of triple point of aluminosilicates, like the Altmus in 1967 carried out the experimental work. He find out the triple point located at 595 degrees centigrade 6.5 kilobar. Richardson et al. In 1968 find the triple point at 620 degrees centigrade 5 kilobar. Newton in 1966 found the triple point at 500 degrees centigrade 4 kilobar. Holdway in 1975 found the triple point at 501 degrees centigrade 3.76 kilobar. In the common rocks, the pressure must have exceeded about 4 kilobar when the almandine garnet is formed in Pelitic rocks. Horsberg and Winkler in 1986 produced almandine garnet by the reaction Fe chloride plus muscovite plus quartz give rise to almandine plus biotite plus minus aluminosilicates plus water, which occur at 500 degrees centigrade 4 kilobar, 600 degrees centigrade 5 kilobar. The upper pressure limit may be given by the reaction albite give rise to jadeite plus quartz, which occur at 200 degrees centigrade 7.5 kilobar, 300 degrees centigrade 9.5 kilobar. Another important reaction is chloride plus albite give rise to glaucophene, carried out by the rover in 1972. As plesioclase is stable in Amphibolite facies and the glaucophene and jadeite are absent, the upper pressure limit may be around 8 kilobar. Thus, it is concluded that in the Amphibolite facies, metamorphism take place at 550 to 750 degrees centigrade at pressure between 4 to 8 kilobar. The course content on the metamorphic intermediate pressure facies begin with the introduction, followed by the description of zones oblique subfaces, the important characteristic minerals in this facies, detailed description of individual zones oblique subfaces, that is Staurolite zone, Kyanite almandine zone, Sillimanite muscovite zone, and finally Sillimanite orthoclase zone, with the help of the ACF, AKF and AFM diagrams, and the mineral assemblages for the peltic, basic and calcareous rocks, important reactions, and finally the physical condition of metamorphism during Amphibolite facies. On the basis of the important reaction, like the Staurolite is formed by reaction chloride plus muscovite plus almandine garnet give rise to Staurolite plus biotite plus quartz plus water, which occur at 540 degrees centigrade 4 kilobar, 565 degrees centigrade 7 kilobar, carried out by Hosek 1969. and breakdown of muscovite in presence of quartz give rise to orthoclase plus sillimanite plus water, which occur at 540 degrees centigrade 1 kilobar to 620 degrees centigrade 3 kilobar, carried out by rover in 1974, indicates the upper stability of this facies and also formation of hypersthene by the breakdown of amphipholite support the upper stability and the beginning of the granulite facies. The reaction Mg amphipholite give rise to anorthosite plus quartz plus water, which occur at 745 degrees centigrade 1 kilobar by Greenwood 1963. Thus, on the basis of detailed study of different zones and also with the support of experimental data, we can conclude during amphibolite facies the temperature varies between 500 to 550 to 750 degrees centigrade and pressure between 4 to 8 kilobar.